Alright, this is my MEGN 200 final project. It's an actively controlled rear aerodynamic element for a track car. In my case, my Mitsubishi Eclipse. This solves the problem of dramatic oversteer, which my car certainly suffers from, and I know several others do as well. This improves that by rotating downwards when you're cornering and braking to increase downforce on the rear of the car, which will increase the normal force on the tires and improve grip. Then, when you straighten back out onto the straight, it'll flatten back out, disengage with the air, and reduce drag, which allows you to go faster in a straight line, which is also important for cars like mine, which have a lack of power. Now, designs similar to this exist on the market today, but they're all highly specific to cars. My goal here was to create a design that could be moved from car to car and has nothing that is componently specific to a certain car. Therefore, you can take this and put it on my Eclipse or a Subaru or any other car you'd like. And here's how it actually works. It's using an Arduino to control everything and using an accelerometer to collect data. In the final design, when this is put on a car, this will be connected to the underside of the trunk, but for now I have it taped to this Hot Wheels just for demonstration purposes. The Arduino also has a couple buttons connected to it. That's just to turn it on and off and do a test cycle. And then we have 4 relays working as an H-bridge to control the higher voltage coming from the car. We have the actual element up here connected to these custom brackets that I designed in SolidWorks, using these, for now, cheap linear actuators that definitely could use an upgrade later on. So, when we want to actually use it, this is its resting state, so when your car is on, it'll be sitting like this. When you get to, your track or maybe a back road that you want to have some fun on, you're going to click that button to turn it on. Then, I'm just going to use moving this Hot Wheel to simulate the accelerations that your car would feel. As you're braking into a corner, it'll rotate downward to an ideal angle that you can set during your track day. And then as you're turning, as demonstrated by the car being on its side, it'll stay in this position as long as you want. Then, when you straighten back out and back onto the straight, it'll flatten back out to reduce drag. Now, we can press this button again to turn it off. The other button here is just a test cycle for before you actually go out on track. You can confirm that everything's working. So it'll rotate up and down a couple times, confirming that the linear actuators, the relays, and the bracketry is all in alignment. So here is the flowchart of how the logic of this program actually works. It's fairly simple, but let's just go through it real quick. There's 2 button inputs. Again, the test cycle button here, when you press it, it runs the test cycle. Couldn't be more simple. The other one is a toggle switch on-off for the whole system. If it's currently on track mode, it'll turn it off into standby mode, which will just leave it right there doing nothing. If it's in standby mode, it'll turn it into track mode, which will continually run this loop right here. So it checks if the braking or turning acceleration exceeds a certain threshold, which you can set in the program depending on your car's setup and when you want it to be engaging. If it doesn't exceed that threshold, the wing will rotate up into 0-degree angle of attack, and if it is exceeding that threshold, it'll rotate wing down to whatever pre-specified angle you want. That really depends on your wing and the speed of the track you're at. Cool. Here's just a pretty crude but effective wiring diagram. Everything's running off the car's electrical system when it goes in the car. So there's the 12 volts coming from the car, well, 12 to 14, depending on the exact condition of it. That goes into 2 places. 1, the linear actuators are directly powered off of that. And 2, that goes into a voltage regulator to power all the lower voltage 5-volt Arduino components. While the Arduino is supposed to be able to take up to 12, because the car system fluctuates a little bit above 12, I did end up burning out one Arduino trying to plug it in directly to the system, so a voltage regulator is necessary. So we'll start at the Arduino here. It's connected to the accelerometer. The accelerometer connects to its own separate power because it runs on 3.3 volts instead of 5, and it connects to the common ground for all of the low voltage things, and then connects to 2 analog pins to send data. Then we have the 2 buttons, again, same ground, and they connect to 2 digital input pins. And then we have my custom-built H-bridge that uses power from the Arduino to run it, as well as 4 inputs there. On the high voltage side of the H-bridge, we have, again, power coming in from the car's electrical system, and then power going out to the linear actuators in the correct pattern to allow it to switch between current flowing one direction causing them to extend, and current flowing the other direction, causing them to retract. And that's pretty much everything.